Okay, so now we've kind of killed off a serious possibility with the Nielsen-Schwann theorem, because suppose we want to implement a family of unitary operators, sigma z acting on qubits. So I'll make sure one equals there. And for theta in some range. So for example, suppose we want theta between 0 and 2 pi. Well, let's first of all write down what that would do to a qubit state. So it would act like this, so that we would have u of theta acting on 0. Okay, so sigma z acting on 0 is just 1. So that would be an e to the I theta 0. And if I take u of theta acting on 1, okay, sigma z acting on 1 is simply minus the 1 state, okay? And so that means that this would simply be equal to e to the minus I theta 1. Now, that would also mean finally that u of theta acting on psi, which I'm going to call u of theta alpha 0 plus beta 1, would just be alpha e to the I theta 0 plus beta e to the minus I theta 1. So that's the set of operators we would like to implement. Now, Nielsen and Schwann tells us that basically we can't do that if it's going to be deterministic. So that means that we're going to have to resort to something else, and what we're going to resort to is a probabilistic processor. So the idea of a probabilistic processor is you send what you want into the processor, you measure something, and if you get one result, you accept the output. If you get a different result, you do not accept the output. So let's see how we can do something like this, and with a probabilistic processor. Now, it turns out that our probabilistic processor is really simple. So it's going to look like this. It's just going to be a C0 gate. Okay, so what we're going to put in here is going to be psi. And here we're going to put in some kind of a program state. It's going to depend on theta. So what kind of program state am I going to put in? Well, I'm going to put in the following. Now, let's trace through what's going to happen here. So we're going to take this, put this thing through the C0. We're now experts on C0 gates because this is real simple. There's only one of them. We were dealing with a circuit with 4 of them, so this should be a piece of cake. So we're going to start with psi, and then the program state. And that's going to be an alpha 0 plus beta 1. And then we're going to have a 1 over square root of 2 here. And we are going to have an e to the I theta 0 plus e to the minus I theta 1. Now, what's the C0 going to do? Well, as you remember, the 0 in the control line of the C0 does absolutely nothing to the state in the target. So if the alpha 0, I'm just going to get this state back again. So this is going to go to, after it goes through the C0, I will get an alpha 0 times 1 over square root of 2 times e to the I theta 0 plus e to the minus I theta 1. And with the beta, now remember when the top line of the C0 gate is a 1, that means that that's going to flip the state down here. The ones are going to go to zeros, and the zeros are going to go to ones. So what's going to happen here is I will get a 1 over square root of 2 times e to the I theta. That's going to become a 1 plus e to the minus I theta, and that's going to become a 0. Okay, so now let's collect things in a certain way. I want to collect things that have first a 0 in the second place. So I have 1 here, and I have 1 over there. So what happens if I do that? So I'm going to have, and I'll pull out the 1 over square root of 2 in front, and then I will have an alpha, and then an e to the I theta, 0. And then for the beta, I'm going to have a plus beta, and then the beta gets an e to the minus I theta, and that is multiplying a 1, and then I have a 0 in the second slot. And then the next thing I want to do is collect the things that have a 1 in the second slot. So that's going to look like 1 over square root of 2 times. Okay, so here I'm going to have, I have a 1 here, so I'm going to get an alpha e to the minus I theta. And then that is going to be times a 0. And then it has the 1 there, but I'll write that in just a minute. And then for the beta is going to have, I have a 1, 1 here, so it will be a beta e to the I theta. And it'll be a 1 times a 1. Now let's see what we've got here. This is what we want to get. I want an alpha e to the I theta 0 plus a beta e to the minus I theta 1. That's exactly what I've got here. But I've got this other term. So, and that gives me something that I don't want. I get alpha times e to the minus I theta instead of plus I theta. And I get a beta times e to the plus I theta instead of a minus I theta. So how do I get rid of this? Well, what I do is I put a detector here, and I only accept if 0 is measured. So if I do that, if I do in fact get a 0, I'm going to get exactly what I want. So if I do get 0, then first qubit is e to the I theta sigma z psi, which is exactly what I wanted. Now, what's the probability that I'm going to get 0? Well, you can work out the details, but this is a unit vector, and this is a unit vector, and they're both multiplied by square root of 2. So the probability that I get a 0 here is 1/2. So half the time, this thing is going to succeed, and it's going to give me the state that I want. And so this is a probabilistic processor. You don't always get what you want, but you know when you do get what you want. And it's possible to increase the probability from 1/2 if I start making the program state bigger, but I'm not going to go into how to do that. And that allows you to have the answer that you want more often. So in the case of a situation where I want to realize something with a continuous parameter, Nielsen and Chuang says I can't do it deterministically, but as we've seen with this little simple example, I can do it probabilistically. And I can make that probability pretty high by sort of making this program bigger, but as I said, I'm not going to tell you how to do that. And so we can realize, with deterministic processors, we can realize a finite number of operations. With a probabilistic processor, we can realize an infinite number of operations with the catch that it's only going to give us the right answer some of the time. So that is really it's a short survey of quantum machines. And just to briefly summarize, what did we do? We first looked at machines that did a specific thing, like the cloner and the U-NOT gate. And then by looking at the cloning circuit, we realized that what we had was something that we could view as kind of a program and data. And in that case, we had 4 possible programs that gave us 4 different operations on the data. And then we went to what Nielsen and Schwang told us, that every time you introduce a new operation, you have to add dimensions to your program space. And that meant really we could only deal with, from a practical point of view, a finite number of operations. And finally, we said, okay, if we want to deal with an infinite number of operations like this here, we can't do it deterministically, but we can do it probabilistically. And we can make the probability pretty high if we make the programs more complicated. So I hope that little survey of quantum machines gives you some idea of what you can do with these things. There are other possibilities out there, but I think this is a good place to stop.